Almost everybody back in their seats. So we're on to the next brain-themed talk, harnessing the power of the brain with metal-oxide memristors.
Memristors, yes. So there is a word missing.
Themis Prodromakis.
Right.
So from the University of Southampton. So please tell us all about it.
Thank you very much. So it's great to be here in this event, and I'll switch a bit gears and try to talk about next generation hardware and what we could do and how we could emulate. So I said, harnessing the power of the brain is a bit bi-directional. So one has to do with how we get inspiration from the human brain and biology for impacting the next generation of technologies, and the second part of this has to do with how can we actually literally tap into the rich functionalities of the human brain. So I'll go through modern electronics challenges, memristor technologies for those who are not aware what they are and what we're doing in my group at Southampton, give some examples of applications, mainly focusing on the computing aspects, so beyond memory, and if we do have time, hopefully we could see what the future could look like with these technologies. So 2018 is definitely a year that we will all be, we will all remember, because it's indeed, we heard about the end of Moore's law, but from my point of view as an electronic sort of manufacturer in a way, researcher, the fact that Global Foundries just a few weeks ago announced that they're halting the 7 nanometer foundry capabilities is really shocking. Is really showing that the end of Moore's law is here indeed. This is one of the things that we have to be aware and do something about it. And on the other side, everyone is talking about AI, and perhaps specifically this year has been the sort of new buzzword for seeing everywhere, specifically in the UK. But there are a couple of editorials as well as loads of different press releases indicating that AI specifically has a hardware problem. So we need to be getting away from the conventional solutions, trying to address the von Neumann bottleneck, where the fundamental design of memory and processing being not collocated is actually constraining what we can do for AI. So let me introduce a bit memristors and what the technology are. So it all started almost 4 decades ago with the chap on the left-hand side, Leon Chua, a professor at UC Berkeley, simply pointing out from a theoretical symmetry argument that there must be a component or something that links charge with flux. As for example, we have a resistor linking voltage with current. And that if that something exists, it will have this sort of pinch hysteresis signature in the current voltage domain. And what was a theoretical prediction almost 10 years, just 10 years ago, in 2008, a team from Hewlett-Packard, led by Stanley Williams, announced in a famous paper in Nature that they found a missing memristor. And obviously, to be frank, they were not the only ones identifying this phenomenon and working on resistive switching in this particular configuration, 2 terminal devices, metal insulator, metal topologies, but they were the ones who successfully identified the link with the theory predicted by Leon Chua. And ever since, there's loads of papers coming out. There is thousands of people working in this domain now. And if you look at the periodic table, these are just a couple of examples that appear that can be useful for memristors. And everything switches. I would say that everything ages essentially, because this inertia that we observe that transcribes memory has to do with the aging of the materials essentially. Specifically in my group, I'm interested in exploiting metal-oxide systems like titanium, niobium and tungsten oxide, specifically for neuromorphic applications because of the rich dynamics, some of which I will show you in a bit. But we're also interested in hafnium, tantalum, as well as silicon oxide, because you get them for free in deep submicron technologies. And I know I started by saying that CMOS scaling has an issue, and CMOS in general, we need to do something about CMOS. But that doesn't mean that we can simply, because memristors came on board, and a new technology comes on board, we could simply sort of throw in the bin 7 decades of development and multi-trillion investments into the electronic sort of industry that we have at the moment. So we're interested in having an interoperable and compatible technologies with CMOS working hand in hand, so we can essentially extend CMOS capabilities. And we do that in, as Errol said, I'm the culprit. We're using these very expensive, not so energy efficient facilities at Southampton. That we're paying about 800k per year in electricity, but it's so expensive because essentially it's a £250 million facility that allow us to fabricate our devices not just in 4-inch wafers but up to full 8-inch wafers, and that put us in a unique position to allow us to collaborate directly with industry. And we just started a program grant in this area where we collaborate with TSMC and integrating our technologies on the back end of their CMOS technologies at full wafer scale. So we develop the technology, the devices at standalone just for experimental purposes, as well as crossbar arrays. And the smallest that ever has been reported in these devices are down to 2 by 2 nanometers, way below the CMOS scaling constraints. Obviously, making one device, it's a challenge, but trying to repeatedly and reliably integrate it and demonstrate a sort of medium scale integration, as in this particular example from my group, is a completely different story. So at least I take pride that we've demonstrated the highest density integration in terms of a crossbar array. This is a 1.4 by 1.4 micron, in which you have actually 1,024 functional devices, and these are devices we fabricate at Southampton. A bit on the understanding, how the technologies work. There are memristors is really, as a definition, a broad church. It includes a variety of different technologies that have to do with the change of their phase, or the formation of conducting filaments within the materials, or the displacement of mobile ions, ionic species. So we've shown in my group before that in a metal-oxide system, like this one, which is titanium oxide, green is titanium and red is oxygen, blue is platinum, so you have your metal insulator metal technology here, that not only you move your oxygen species across, oxygen vacancies, but also titania interstitials, therefore you fall in the first category. In doing that, you're reducing locally your titanium oxide in one of the Magnelli phases, and macroscopically you're creating these conductive filaments. But this formation of conductive filaments that the majority of groups are exploiting for memristive technologies is not something that can reliably be used, and you could see this here, how you end up with even the delamination of the top electrodes, and something that leads into irreversible switching. Ideally, you need to be in this reversible switching operation regime. So what we have done in my group, we've went away from all these 3 different mechanisms, and we've introduced, kind of invented a fourth one, which is not so aggressive and has to do with an interfacial barrier control, and it's much less destructive, and also addresses a different issue. If you have a single metal oxide system within your titanium oxide memristor, in this particular case, although you might be able to switch it on and off a couple of times, it might actually undergo some drift over the longer period of time. So that's something that puts constraints on how you could use these technologies. By engineering the device stack and having a different bilayers of materials, so we've studied a number of different stacks, all metal oxides with titanium oxide as the core kind of switching material. We've demonstrated that we can fix this issue, and by fixing this issue reliably, we can push further the analog performance of the devices into a remarkable, even up to 7 bits actually, even up to 128 discernible memory states you can actually have within a single device, not zeros and ones anymore. What I'm showing here is the median response of the 1 kilobit array that we have at Southampton, which is 5.5 bits. and better. And if you don't trust me, if this is reliable and discernible, and also in the longer term, all you need to do is to look at the retention characteristics for over 8 hours among randomly selected neighboring sort of memory states that are nicely stored non-volatilely. What you can do with this is you can essentially have a tunable load, and you can arbitrarily program it into different resistive states, only at a fraction of the energy consumption that you would have compared to conventional systems. So in this case, it takes picojoules of energy. Now, how do you really use these devices? There is a so-called concern that you can access these memory states in different ways. So either having a pulse of a train of pulses essentially at a fixed voltage and a fixed pulse duration, or you can have a single pulse at wider duration that gets you exactly to the same resistive state, or you can have a narrower pulse but of higher amplitude. So this integrating feature is posing a challenge for the memory community, known as the time voltage dilemma. But here we actually see an opportunity for the applications I'm going to present now. So I'm going to show 3 specific demonstrators. Obviously, this capabilities as technological capabilities great for next generation memory, as you can imagine. But I'll try to put the focus more on some recent work that we have done, where we're exploiting the devices mainly for computation. So example first has to do with what also Steve introduced earlier on. Whenever you have a synapse, essentially you can treat it as an engineer. Abstractly, I'm treating it as a 2-terminal device. You have a presynaptic and a postsynaptic terminal, and you have a barrier in between, which is nothing than your synaptic cleft, where all the magic happens. You have the release of neurotransmitters, and that essentially modulates the conductance of your synapse. So whenever I see this, I feel like I'm seeing this, which is nothing more than a cross-section of our memoristic technologies, where you have a top electrode, bottom electrode, emulating, if you like, the pre and postsynaptic terminals, and in between still you have a barrier. You have your metal-oxide system, and in fact you're using similar dynamics. You're still using diffusion, the diffusion of ionic species to modulate its conductance. So first example has to do with demonstrating unsupervised learning. So we've looked at different ways that these devices can actually be programmed. And in this particular case, we find the unsupervised learning to be exciting, more exciting at least compared to the conventional supervised learning problems, because it's something that you could use for embedded kind of applications where the data clusters drift over time, and the system can learn by itself of what it's looking for. In this particular case, we encoded conditional probabilities into the resistive states of a number of different devices, simply by having a number of potentiating and depressing events existing within the different signals that we were looking, that affect how the conductance of the devices drifts over time. Once you have that, you can put it in a winner-take-all network, and those neurons will essentially specialize in looking for specific patterns that exist in the signals that you're handling. And it handles mistakes actually rather well, surprisingly rather well. So you could see initial and final response of this system, and the beauty, as I said, is that this system can actually adapt over time. If the class centers drift over time, it could forget and relearn like different patterns and specialize in looking at different patterns. So this was published about 2 years ago in Nature Comms. Is one of the examples. Switching gears into a second example, which has to do a bit more with a challenge around processing big data in real time and on the node. Okay, a challenge that exists for electrophysiology, and excuse me if some of you are already aware of all of this, but I just try to give an abstract kind of overview and introduction of the problem. So on one side, you want to first of all monitor at large scale neural activity, and you have to deal with a system that looks like that. You have loads of missing neurons and synaptic connections formed all over the place. Imagine you have that also now in the human brain. So you have this massive piece of jelly sort of, so it's interfacing to that as well is a challenge. So what we need to know from this, electrophysiologists need to know 2 things. First of all, is there any activity, the so-called spike detection, detecting the events, the spiking events of individual neurons, but they also want to know which specific neuron is actually spiking, which is the spike sorting. In an analogy, it's like you have a room full of people and every single one of you is a neuron. So what I need to know is I need to develop a microphone first of all that will pick up some noise, and therefore I will know that there is some activity in the room. But secondly, I would like to be able to have sort of different patterns. The voice is recognizing the voices of all the individuals in here. So if I need to know if Errol is in here, I need to have his voice somehow stored somewhere and compare whatever I detect with that. And the voice is essentially the neuronal signature. So the interfacing, it could be very different obviously in both cases, but in all cases you do need the sound console or a neural processor, and the challenge, as you could appreciate, has to do with the power consumption you need to spend for dealing with this problem, especially if you're looking at hundreds or thousands of channels simultaneously doing this job, bandwidth, area, and the complexity. What we've done is we kind of turned the problem around and said, this is what our technologies do. This is what a single memory store does. You want to be above this soft breakdown sort of switching threshold where the magic happens, and you have this reversible switching. Forget about that. This is something that we just need to stay away so that we don't, mess up with the lifetime of our devices. But below the switching threshold, nothing happens. So if you start ramping up the stimuli voltage in here, you could see there are the soft sort of breakdown switching thresholds in positive and negative polarities, and the moment that you exceed this threshold, you start observing this non-volatile change in the conductance of your individual devices. Okay. Now, how is this useful? I mean, that you can replot as something like that. So you have a dead zone, and ideally in neuronal signals that you will detect from via multi-transistor array, for example, or a multi-electrode array, they look like this in the first here instance. So you have the different events that you need to make sure that you record that there has been an event. So ideally what we've done is something very simple, taking the signal, feeding it into here, and biasing our devices with these particular signals, assuming that these events will exceed the switching threshold of our devices, and essentially they will transduce every single event as a change in the conductance. Why do you want to do that? Simply because it's done in a non-volatile way. It's done passively, and you don't have to frequently monitor, have a continuously on monitoring system that is checking whether there's been a spike or not. You can afford to leave your devices there passively interrogating what the activity of the system, and then whenever you wish, depending on the application that you have in mind and how frequent you want to look at what sort of activity there has been in the network, you could go and say, all right, how much your conductance has changed, and that will be an indication of how active this has been. So in this particular case, we did a kind of blind test because we took the signals from our collaborators Max Planck. We did not intentionally, we did not ask of how many events we have in here, and we said let's invert it and concatenate it 4 times to see, whether we can really have a measure of these events, and you could see that it's truly reversible. Once you have that, you can start using the scaling benefits of the technology, so start putting these in big arrays, and then you have a sort of building a high definition, if you like, analytical platform for these cells. So what you see here are 3 neurons sitting on top of these crossbar arrays, essentially contributing to change the conductance over time. Now, I've mentioned the time voltage dilemma, which is a challenge, but here is really an opportunity. The first part from what I've discussed just now about this biosignal detection deals with the spike detection. But in fact, we know, because of the time voltage dilemma, that it's not just the amplitude of a spiking event or whatever biasing protocol you have in place that modulates the conductance of your device. Essentially, it's the integral of that affects how much the conductance of your device changes over time, which kind of got us thinking that these different types of spiking activity is essentially what we need to do the template matching at. And the way that you will typically do that in a standard electrophysiology laboratory is you will monitor all the data, ship it out in a way, because bandwidth is a big issue there. We're talking of an excessive amount of data. You typically need some specialized optocouplers to do that, and get the data template munched by a supercomputer externally. Here, however, you have a single nanometer scale device that does the job for you. And here is the early proof, where you can have all these different types of spiking events. And as you start from biasing these devices through a fixed initial resistive state, you could then compare it with respect to the initial resistive state and see, how much the conductance has actually changed. And naturally, without us doing any effort, these clusters appear. So you have spike sorting for free as well. And last but not least, switching gears into a third example, which is a bit more not so bio-inspired, but what you can actually do with the technologies, and shows ways that you can utilize the technology in energy efficient ways. Our world is truly analog, and we need to be dealing with analog signals. So we don't smell or see or sense with a fixed precision. Nonetheless, our electronics nowadays is mainly digital for a very good reason, because of the scaling and because of the energy benefits that we actually have from the digital paradigm. So if you look traditionally, we have an analog design paradigm and a digital design paradigm, and the so-called sort of mixed signal design paradigm, right? But the mixed signal is exactly what the words say. The mixing is done at the signal level. The technologies below still remain separate, and that is putting extra constraints in terms of how much further we could push the systems, this design approach, for achieving better energy performance as well as minimizing latencies. So what we have done is we took a standard primitive, cell, like a digital inverter, the all very well known transfer characteristics of that. So we put the question, what would actually happen if we were to take these analog memory technologies that we fabricate and we integrate it here locally? So surprisingly, what happens is you skew the characteristics of your inverter, essentially creating an analog gate. All right. And by the way, I guess all of these slides will be available later on, so you have that. So you have an analog computation, but at the cost of digital, which is really great. And the so-called charge-based computing comes up naturally in a way. Not only you have that, you have the capability of reconfiguring on the spot these memory devices there very, very locally. And that allows you to reconfigure, obviously, the transfer characteristics of your inverter, of your analog gate now. So what you can do with this, you can start creating very simple circuits around that will utilize this concept as a classifier, but as a very efficient classifier that is passively sitting there. The moment that you store, let's say, a value in these devices, by the way, that can be a single device only, and the moment that you're actually detecting that value as it comes in, you're hitting the target and you're raising a flag. You say, boom, I'm here. The beauty of this approach, however, is that when you're off target, this extremely simple concept tells you which way you need to move your receptive field in order to identify where the target is, the right target. And I guess this is kind of what made this approach, in a way, that this idea of fusing analog and digital, really, but at a technology level, is what kind of made this get accepted a few weeks ago in Nature Comms. And here's an application of what you could do. You could take some of those analog gates now and start tessellating them, and do also the spike sorting application I've shown to you earlier on, where you can simply go and program all these different values that you can have in a specific type of event into these different devices in a tech cell, and identify that. So I didn't expect that I will make it in time, but we still have 2 minutes perhaps, and what the future could look like. So if you are actually able to put these devices and collocate them with mainstream CMOS technologies and utilize them fully, you can there are significant benefits in terms of power consumption, in terms of what sort of compression you could get, absolutely benefits in terms of cheap real estate, but also how do you utilize this? It's very versatilely utilized and to allow you to do big data processing in real time, but also maintain the granularity of the extracted information, as I've shown in the example of the biosignal processing at the edge. And one kind of sort of concept that could appear naturally if you have these super efficient classifiers is that you could get into a point where you won't need to have, for example, your mobile phone, you would not need to have the connectivity to the cloud in order to allow you to utilize Siri to run here locally. And why that could be important, I could think of various examples. For example, going into China, and I always use my iTranslate application that I love. I would not need to utilize my roaming in order to use this. But privacy is also extremely important because if you really want to have a rather secure way of dealing with data, well, you should not share your data in the first instance. So having efficient classifiers like that really allow you to do the processing on the spot could empower users in the longer term with getting the privacy in the data. So I would like to acknowledge obviously our funders for supporting the work, and this is the team at Southampton at the moment that has contributed into the different sort of pieces of work that I've shown here. Thank you very much for your attention.
Let people think that Southampton looks like that.
We're a truly international group, so
Absolutely.
we're all over the place.
We have time for just a few questions. So, thumbs up, fire away.
Yeah, I have one for you about the spike sorting idea. I mean, it appears to me, maybe I didn't fully understand it, but it seems to be just sensitive to the area of the spike. So if you had spikes that are all roughly the same area, that wouldn't work, would it?
It is a problem. You're right, but you could actually utilize a number of different ways to do that. The stuff I didn't show is how do you precondition the signals in order for this to work. So you have, first of all, the amplification factor you can include, and also an offset that you could give to your signals before you biasing the devices with. And a third idea that we're working on, and that's a collaboration with GlaxoSmithKline and specifically Galvani Bioelectronics. We're working on how do we exploit the variability of devices that you have, so have multiple devices doing the same job. So there are a couple of ideas. It's still a primitive kind of, a first concept, if you like, demonstrated. But what I wanted to really highlight is that it's really possible with just relying on the physics, the underpinning physics of these memoristic technologies, to do something that is otherwise considered computationally demanding.
More questions? There's going to be plenty of time in the breaks and lunch to follow up. That's probably the easiest. So let's give Themis a hand again.
Thank you.